one slide from the former presentation that has to do with the difficulty of building the right system, that is building a system that really mirrors what the users want. So to go from a large universe of discourse and turn that into a much smaller conceptual model is a bit of art. And to do this in this presentation, we are going to look at modeling patterns and other data abstractions to help us create good models and good and big enough and small enough classes. So how do we start to model? Well, I've hinted that we're going to use modeling patterns, but before that, let's see what resources we have when we start to model. In the real situation, we will most definitely interview users. We will read manuals and manuals and manuals. We will perhaps study old systems, legacy systems, and speak not only to users in general, but users in different levels in an organization. There may be different demands on a top level compared to a lower level. For instance, a secretary to a doctor may think that the system should contain certain requirements, while the doctor might think that the system should contain other requirements, and so on. But very often, and especially in a school situation where we're learning, we do not have access to real organizations, real people, but we have to rely on textual descriptions of the systems to be modeled. So the problem can be sometimes to analyze very large chunks of text. Texts are composed of verbs, nouns, adjectives, and so on. Those can sometimes be mapped onto different parts of classes. We'll also try to map texts upon modeling patterns and other data abstractions. If we start by analyzing 4 sentences, where the focus will be that the same word appears many times but have rather different meanings. This is also called homonyms, where one and the same word or phrase have different interpretations. So how is the word book used in the sentences below? Jules Verne wrote many books, one of which has the title The Children of Captain Grant. That's the first sentence, and books here is focus. Then the second sentence is the library in Vällingby has many books. Second example of a book. Third example is if The Children of Captain Grant was printed in A4 format, the number of pages in a printed copy will be 100. There is no book here, but somehow it's about books anyway. The name of a successful bookkeeper was Pasquioli. So we have book, the term book, in at least 3 of our 4 sentences, and yet it seems that it's not the same type of artifact that we are speaking of. Sometimes we are speaking about an abstract book, the literary piece of art by Jules Verne, The Children of Captain Grant, and sometimes we are speaking about a physical book that Captain Grant's children is perhaps printed in a particular format, and then there will be a number of copies. And the last sentence, bookkeeper, and that there was a famous bookkeeper that was called Pasquioli, then book means something completely different. It means actually account. So we can encounter, when we try to analyze text to build conceptual models, one and the same term may mean different things, homonyms. We also have synonyms. That's when different terms actually map onto perhaps the same or not the same concept. Fire and let go. Do you think that means the same thing? Labor giver and labor buyer, is that the same thing? It's different terms obviously, but do they mean the same things, these terms? And student and pupil, is that the same thing? Could be in some domains. In the Swedish educational domain, it's not actually. A student is what you become when you have successfully finished high school. A pupil, then you have not yet finished high school. So only students, for instance, can be admitted to university. And of course, this is also complicated by the fact that meanings of words or terms may differ heavily across organizational and institutional borders. So, if we have only large walls of text and we are going to use this to create a good class diagram, how do we do it, and what is good classes? Well, classes should be small enough to be useful and self-contained and easy to understand, but we can't have too many of them, because then the conceptual schema will get too cluttered and hard to understand. So I've tried to, in this slide, to contrast one enormous class called the system with 10 million very important attributes. That is of course not good. That's not a good conceptual schema with one enormous class in it. But it's not good also to have very small classes with perhaps only one attribute each, and then very many of them. A, A1, A2 and so on, from down to Z something. Yeah, and to our help in finding these good classes, we will encounter 3 modeling patterns, and also I think 2 rules of thumbs that will be presented in the coming slides. One modeling pattern is called inheritance, and that is when you have a hierarchy of classes which are more and more specialized the longer down in the hierarchy you go. For instance, we can take the next slide. UML classes. On the highest level, on the root level, we have an animal. Animal can be divided into mammals and birds. Mammals seem to be able to be divided into herbivores and carnivores, those who eat meat and those who eat vegetables. And the herbivores can be divided into hoofed animals and rodents. And then we have some leaf level classes, namely moose and rabbits. And a leaf level carnivore class is dachshund. A leaf level bird is penguin. And why do we create a hierarchy like this? I mean, we could have just one enormous big class animal, or we could divide animal into a number of so-called subclasses. And when do we do that, and why is that good, or when is it good to do so? So, a motivating example in terms of when to use inheritance or generalization specialization, so which it is also called. So to my help, I have a first small example of a small class, but a class that is still too big. So the class is called animal, and it has 2 attributes, name and taxation sum. And the name has a cardinality constraint, which is 1, ... 1. That means that the name always exists for the animal. The minimum value is 1. There must always be a name. And the number of names that an animal can have is at most 1. So 1, ... 1. The other attribute is a bit ambiguous. It's called taxation sum. And it has a cardinality constraint of 0, ... 1. And this means that not all animals have taxation sums. There are some animals for which the attribute taxation sum does not apply. Hence, we have a minimum value of 0 on taxation sum. So, what if we now have dogs and cats in the database? Do all these animals really have a taxation sum related to them? No, they don't, as I have indicated. In Sweden today, actually no animal or no pet has a taxation sum, but some 20 years ago, dogs were taxed. So dogs, if you were a pet owner and the pet was a dog, then you had to pay a certain amount of tax. And since not cats and other pets had to pay any taxation sum, when we model taxation sum in a class that is called animal, we cannot have a minimum value that is 1. It has to be a 0, since not all animals have a taxation sum. Actually, we have a word for attributes with a minimum value of 0. They are called partial attributes. So a partial attribute is an attribute with minimum value equal to 0. A total attribute, on the other hand, that's an attribute with a minimum value that is larger than 0. If we want to create classes where the attributes apply, which they should, to all individuals of a certain class, then we should strive to have all attributes as total. That is, the minimum value for all attributes in a class should be 1. The minimum value should be 1. And one way of accomplishing this is to divide the class into an inheritance hierarchy. In this case, I have divided animal into 2 subclasses, dogs and cats. And then we put whatever attribute or attributes, if we have several, that are partial, that is, they have a minimum value of 0, then we put them into the class where they will not be partial any longer. That is, that they will have a minimum value of 1. And in this case, it's rather easy. The dogs had a taxation sum, so we move the attribute taxation sum from animal to dog. So dog now has this attribute instead of animal, and cat doesn't have any attribute at all. But inheritance hierarchy means that the subclasses are related to the superclass via a so-called ISA relationship. And this means that both cat and dog relates to exactly 1 animal each, 1.1 animal each. And this means that the cat will relate to 1 animal, and then we can actually know the name of the cat. We usually say that the cat inherits the name from the superclass animal. It is, of course, so that the name attribute resides in the class animal, but we can reach the name attribute from both dog and cat. They inherit the name attribute. And then class dog has yet another attribute, but now that attribute is a total attribute, 1.1, since dogs, at least at some point in time in Sweden, were taxated. The root class of an generalization, specialization, or inheritance hierarchy is called the superclass, and the classes that are under the superclass is called subclasses. And ideally, we say that subclasses should be mutually exclusive. That is, one individual should not be able to be an instance of both classes at the same time. And this, of course, is true for dog and cat. If I have a dog Fido, it cannot be a dog and a cat simultaneously. Also, we want our subclasses to be what we call exhaustive with respect to the superclass. And that means that the subclasses should cover all instances of a superclass. This is not the case with dog and cat. Obviously, there are other animals than dogs and cats. But we could add another subclass called other pets, who is animal, and then we would have an exhaustive structure. Let's look a bit into this ISA relationship. What does it mean? Well, you sort of hear what it means. A dog is an animal and a cat is an animal. But what are the multiplicities or cardinalities for the ISA relationship? They are as follows, as you can see in red. So a dog relates to one animal, and an animal doesn't necessarily relate to a dog. An animal could be a cat, for instance. So an animal doesn't have to be a dog. Therefore, the cardinality for the roll from animal to dog, the minimum value is 0. And an animal could relate, an animal individual, I shall say, Fido, relates to at most one dog. And likewise for cats then. So a animal relates to 0.1 cats, and a cat relates to 1.1 animal. We don't use these cardinalities when we write an ISA relationship. The syntax for an ISA relationship assumes these cardinalities, so it's enough to draw the ISA relationship, that is a relationship with a hollow arrow, and sometimes we write ISA as well. Then these cardinalities are assumed, so we do not need to notate them in the schedule. That was our first modeling pattern. Before I go to the other modeling pattern, I would like to take the chance to speak a bit about how we relate classes in general. We do it via associations, and now, up until now, you have seen two associations, the usual association and an ISA association. Please take a look at these two conceptual schemas in the form of two UML class diagrams. They are meant to model the same thing, but in the first schema we have one extra association, or one more association compared to the second schema. In the first schema we have dances as a class, and we have persons as a class, and we have a performance, which means that a certain person dances a certain dance and does this at a certain date. And then we have an assessment of the dancing. So someone judges how good the dance performance was and sets a grade, and that person who does the judging is a person, and this is in schema 1 denoted via an association called judge towards person. And we can see that there is one person who judges the assessment, and a person could judge several assessments and not necessarily any. One thing to say here is that when we use the symbol 1, it actually means it's a shorthand for 1.1. I think you have seen this in other UML presentations. So a 1 stands for 1.1, minimum value 1, maximum value 1. Compare this schema 1 to schema 2. It does the same thing, but it does it in another and inferior way. So instead of having an association from assessment to person, we now have an attribute called judge. Does it work? Yes, it does. But it's less well done compared to the first schema. When we want to connect two classes, we should do it through associations. And why is that? That is because if we connect classes through attributes, which can be done, the schema becomes much harder to understand. We could actually omit all of the associations in schema 2. Instead of dance as an association between performance and dance, we could have, in class performance, we could have a dance type, or several dance types. And we could also have several persons. An assessment, we could, instead of relating performance and assessment, we could have attributes for this. In the worst case, the whole schema could collapse into one big class. But that is very, 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 very hard to understand what such a class means. So therefore, we use associations to connect classes, and we should do this every time. We should never have an attribute that stands for an association. If two classes are related somehow, show it with an association, not with an attribute. The wrong order. I wanted to say something also about attributes that are unique. If we have a student and the student class, and this student class has three attributes: personal number, name, and email. And we have modeled the cardinalities of the class. Then we still don't know what identifies an instance of a class. In order to do that, we must somehow model what attribute or what combination of attribute that uniquely identifies a class. And one way of doing that is simply to write unique after the cardinality constraints. And sometimes if two attributes together are unique, then you can say that they are unique together. You can just denote them as that. So, let's turn into the second modeling pattern. Remember that our first modeling pattern was inheritance. Let's look at the modeling pattern that is called reification. Reification has to do with finding associations that should be turned into classes under certain circumstances. Here, as an example, I have two classes, illness and treatment. And a treatment can cure many illnesses, and a treatment, if it is a treatment, must cure at least one illness. An illness, on the other hand, may be incurable, that is, it has a 0 as minimum value in its role. And an illness like influenza can be cured by many different treatments, I hope. Sometimes this is enough. This is the only thing we want to model about illnesses and treatments, and then this schema is good. But sometimes, in this particular instance especially, we might want to model something extra. For instance, how well a certain treatment treats a certain illness. And if we try to put this information in either illness or treatment, it will be wrong. If I put some kind of percentage in illness, then I don't know, since an illness can be treated by many treatments, then I don't know if a certain percent has to do with a certain treatment or not. If influenza can be treated by some kind of treatment 1 and treatment 2, then if I have a percentage here, I don't know the success rate if it is for treatment 1 or treatment 2. And the same goes if I put success rate or some percentage in treatment. I don't know for what illness. There are many illnesses a certain treatment, like for instance penicillin, can treat. And the problem here is that we have a many-to-many association, where the association in itself actually contains an attribute. There's a property of the association. And there are several ways to solve this in UML. What I'm showing here is a so-called reification class. That is, to put an ordinary class between the two original classes that were used to be connected with a many-to-many association. And then you create two new associations from the new class to the first original class, and another association from the new class to the second original class. And then we just use the old cardinalities. If an illness could be treated by several or many treatments, now an illness can be treated by several or many cures. And if a treatment could treat one or many illnesses, now a treatment is related to one or many cures. So the step is to create a new class, put the attribute that belong to the many-to-many association in the class, create two new associations with the same cardinalities as before, plus a 1.1 in each end of the new associations. So this reified class always points to 1.1 of the first original class and 1.1 of the second original class. Let's do an example here. Exercise reification. Extend the conceptual schema above so that it can represent that a certain person has entered a certain club at a certain date. And now we So if we are to extend this conceptual schema, this UML class schema, so that a person can enter a certain club at a certain date, then we cannot put this date thing in class person. And that is because even if we put several dates for a person, we don't know which club they refer to. If we enter the Lions in the if we have a date that says 21st of March 2004 and another date that is 2019, how do we know for which club, Lions or Rotary? So it doesn't work to extend the schema by just an attribute. And neither does it work to extend the schema by putting the same attribute in the other class that is in club, because a club is related to very many persons. And if I put a number of dates into a club, I don't know for which person a certain date applies. So, the solution is to use reification, just like we did with illness and treatment. So, the solution is to reify the many-to-many relationship between person and club. So we remove the original many-to-many relationship. The many-to-many association is another word for the same thing. And then we create a new class called membership, for instance. And then we can put this attribute that doesn't belong to person, it doesn't belong to club, but it belongs to both, in the new so-called reified class. And now we have a new class that replaces a relationship, so we must relate this class to the two original classes. And if a person, we will reuse the original association. So if a person used to have 0 or many clubs, then a person now has 0 or many membership. And if a club used to have one dot many memberships, then a club now has minimum 1 membership, but possibly several. And the other cardinality out from the new class is always 1 to both original classes. So it's a sort of a procedure. Remove the old relationship that was M to M, replace it with a new class, put an attribute into the class, an attribute that sort of relates to the two original classes, and then connect the new class with the two original classing, reusing the cardinalities of the two roles in the original association. And this could be applied to any many-to-many association that has properties of its own. This is important. So we don't reify just any old many-to-many association. Only when the many-to-many association has properties of its own, we need to reify it, that is, turn it into a class. And now I have only one modeling pattern left to discuss. And I will go back to the discussion about homonyms before. How could a certain word like book be used in very many, to have very many meanings? I mean, we had 3 different concepts that actually meant 3 different things in one class. Social 1 wrote abstract books. There's nothing concrete about the artwork. I mean, the book, the content of the book. But the book could also be concrete, so it could be a physical book. And we could also use the book in combinations with other words like bookkeeper. A famous bookkeeper was Luca Pacioli. And obviously these 3, where book is concerned, these 3 books mean different things. The physical book, the abstract book, and an account, completely different things. And if we try to model all of these concepts, since they are all called book in one and the same class, then we will end up with something like I have done here. Book. There's things like author, title, weight, number of pages, mean weight perhaps, and keeper name. Question mark, question mark. And as you can see, 4 of these attributes does not belong to all instances of a book. For instance, abstract book that is literary pieces of art, they do not have a weight, they do not have a number of pages. Mean weight perhaps they could have. If you print if you count all the printed books of Captain Grant's children, then they may have a mean weight if you combine all the weights and divide them by the number of printed books. And keeper name has nothing to do with books in general. That's here. Book is just a synonym for count. So if we have partial attributes as we have here, we know since before now that one way of solving this is to divide book into an ISA hierarchy. The question is an ISA hierarchy really applicable here? ISA hierarchies, as you remember, denoted subsets of things. For instance, we had animal that could divide it into cats and dogs. But when it comes to abstract books and physical books, I mean, those are not subsets of books. They're different types of things, really. And printed book have certain properties that has not so much to do with abstract books. So let's look at another pattern, the template copy or power. So a template copy structure, or power types as it is called, or category classes. Here you can see that certain objects may be seen as template for other objects. And those other objects that can use the templates are called copies. So in this case, for instance, we have a power type which is called book. And it has attributes like author, title, and maybe mean weight. Then we have a printed book, and let's call it copy. And the printed book has also properties. It has weight, and it has number of pages. And the copy relates to exactly one power type, one book. And in that case, it's very close to an ISA relationship, for a subtype is also related to one supertype. But in the other direction, it's not the same. One book, one template, one abstract book, one literary piece of art does not refer to one printed book only, but many. And that was not the case with ISA relationships. So maybe we should compare the two. So another example of a power type. And remember that the rule of thumb is that all attributes in a class should be total, that is, that the minimum value should be 1. And we can accomplish this either by using ISA hierarchies or, as we are going to do now, use power type hierarchies. So, a motivating example then. How is the word tiger used in the sentences below? Shere Khan is a tiger who lives at London Zoo. The mean weight of the tiger is 300 pounds. The tiger Shere Khan weighs 400 pounds. And the habitat of the tiger is the Far East. If we just model all of these 4 sentences, or the information that we can retrieve from these 4 sentences, into one class, we might end up with something at the left hand side here. Animal with name, address, weight, mean weight, area, and species name. I think I've gotten all the attributes that are mentioned here, but all of them seems to be partial. We seem to have tigers that are abstract, or more to deal with the tiger species, and then we have individual tigers that has certain properties. So I mean, a tiger doesn't have a mean weight, it has a weight. And an individual tiger doesn't have a habitat, it might live in London Zoo and not in the Far East. So let's divide this too big animal class into 2 new classes using power types, and then we will have something like this. So we have animal, which is a copy class, and we have species, which is a power type. Or the animal properties, that is the individual properties, we put them in animal, and then they all become total. So an individual animal has a name, for instance Shere Khan, it has an address, it could perhaps live in London Zoo, it weighs something, For instance, we have a big tiger weighing 400 pounds. And then these individual animals are related to exactly one species. Minimum one, maximum one species. And the species has a species name. The species live in some type of area, could be the forest. And the species has a mean weight. It seems that the tiger species mean weight is 300 pounds. Even if there, of course, are both bigger and smaller individual tigers. So here both animal and species are two classes where all the properties are total. That means that all properties actually belong to all instances, each and every instance of the classes, which is good. Then these attributes are sort of right for each class. Partial attributes, on the other hand, indicates that the attributes are only right for some individuals of the class. And if we go to the next, so we could perhaps coin a rule of thumb here. All attributes in a class should be total. That is, minimum value should be 1, meaning that all the attributes that is modeled in a class really belongs to each and every individual of that class. And we can accomplish this by either using ISA hierarchies, that is, we take a class and divide it into subclasses, or we could divide the class using power type hierarchies, as we have seen. And also, these are two modeling patterns. Nothing says that we can't combine them. An example of this is can be seen here. So the printed book relates to a copy, relates to exactly one abstract book. An abstract book relates to many printed books, many copies. And then the printed books perhaps could be of different types. Printed books can be framed, in which case they have some kind of thread binding, a binding type. Or the printed books could be printed in pockets, and then they are not sewn together. So that if we tried to put binding type in printed book, in the printed book class, then the binding type would be 0.1, since pockets do not have a binding type. But by dividing printed book into framed books and pocket books, we can put binding type in the right class and accomplish this rule of thumb that the minimum value should be 1. Summary modeling mechanisms. We have looked at classifications, that is how we go from a domain and creates a class. Then we have looked at 3 modeling patterns: inheritance, generalization, specialization. Generalization, specialization is a synonym for the word or the term inheritance. We have looked at the reification pattern, and we have looked at power type copy categorizations. Are there more data abstractions or modeling patterns than this? Yes, there are, but these 3 are very common and very important and serves us very well when we start creating good, useful and easy to use conceptual models. Thank you.